him. Can you show his short bibliography? Okay, we couldn't able to show your biography. You can you can make it yourself, please, and you can start your presentation.
Okay, no problem. I'm Savvas Vassiliadis. I come from Athens, Greece, from the University of West Attica. And I would like to thank you for your invitation, especially regards to my good colleagues and friends, Ali and Yusuf and Omer. And I'm really happy to join your conference here. So I will start my presentation by sharing my screen. You cannot start. I cannot start. Okay. Now, normally I should start. I hope you can see my screen now.
Yes, Professor, we can see.
Okay. The title of my presentation is the modeling of the textile structures from the approach to the reality.
Professor,
Yes,
sorry, we need to make full screen. Your presentation, you can make it full screen?
Full screen, yeah, it is full screen for me. I hope it will come for you as well.
Okay, we can continue.
Okay. So the title is Modeling the Textile Structures from the Approach to the Reality, trying to saying that the first approaches were very optimistic and, unfortunately, they were not that precise. However, slowly, by the evolution of the tools we use, we were able to approach the reality. And we will see all this path now.
Professor, sorry
yes,
again, but we are not able to see your another slides. I think you shared with us with your full screen. You can share again your presentation.
Yes, please. Your new share. Once again.
Please. Okay, please share again.
Let's try once again. Now it's not full screen. Maybe it's way better.
Please make it next slide. I try to understand. We are able to see.
It's okay now?
No, we are now in first page.
Maybe it will take some time to renew it.
Can you share?
See if it will work.
Yes, can you share your full screen of computer?
Yes, this is what I do. You mean to?
I mean computer screen.
I will try, yes. The whole screen.
Okay, now we are able to see. You can continue.
Okay, so the path of my presentation is to show the existing methods and models, and then to go to the most modern approaches in order to simulate the viscoelastic behavior of 3D spatial fabrics, where it is really important, this viscoelastic study. And now you can see two airships I hope so. Left side is the airship built by Siemens. Right side is the airship built by Zeppelin. The Zeppelin was the initiator of these big airships, but after a while, Siemens got the idea to compete to the Zeppelin airships, and they had an initially clever idea by removing the metallic parts inside of the airship, since the pressure was high, so practically under normal conditions there was no compression forces, and they had constructed these airships without these rigid metallic parts inside. They did it. However, they faced some problems. They had something like 40 flights over the sky of Berlin. Zeppelin himself has made a trip using the Siemens airship, and it was promising. However, they faced some problems because the fabric of the airship was behaving strange, especially during the winds. It was bent, it was deformed, and so on. And this exactly, these phenomena have initiated a very important study of the structural modeling of the textile fabrics. You'll see in the left side of the screen is the first published scientific work about the modeling of the textile fabrics. It was from Rudolf Haas. This person was the chief engineer of Siemens in the project of these non-rigid balloons. Because of the First World War, this publication has been lost. Many years later, this publication has been made in 1912. Many years later, 1935, the first known, well-known scientific publication arrived from Pierce, and only late, maybe 10 years ago, the first publication has been found, and we realize that they are almost identical. What we can see is that they consider the yarns as continuum bodies, ideal, that means fully elastic, with perfect geometry. That means we had the first approach, but this approach was, of course, not close to the reality. There is a lot of work done on this field. Kemp arrived with a better, let's say, more realistic model. They call it horse race. Horse race. It was the yarn were considered as compressed horse race model. After that, Kawabata with the sawtooth model, and Herle with lens-like cross sections. The more realistic the models were, the more complex were the constituting applications concerning the geometry and also the mechanical behavior. Practically, we were going up to more realistic, let's say, representations, but the solution of the models was almost impossible. There was so much complex. In these late 70s, beginning of 80s, we had the first computational modeling in engineering. You know, finite element model methods came in use, and we have really very important and powerful tools in many engineering sectors, in civil, in mechanical, in electrical, in naval. In every engineering sector, we have really very good and powerful tools. And we cannot imagine that today a building will be designed without the use of these methods, or a machine will be designed without the use of these methods. They are really very versatile, very precise models, and they are very much in use today. However, in textiles, we are not in the same situation. We are under construction. We are working in this direction. Why not concluded to really final end user tools? Because we have in our field very important effect of the non-linearities. We have geometrical and material non-linearities. We have multiple levels of integration. We have fibers, then the fibers are combined to have yarns. Yarns are combined to have fabrics. Fabrics combined to have clothes, and so on. We have multi-body structures, that means many objects in touch and in friction. We have non-isotropic behavior. So all the catastrophe of the world is here. The most difficult problems in mechanics are here. This is the reason we have a delay, and we are still continuing the research towards these computer-aided engineering tools. I'm going to show you some attempts of my lab. We have studied the modeling of the mechanical behavior of yarns using finite element methods. Of course, you will see that we discuss about filaments and not staple fibers. It's much more difficult to discuss about stable fibers. And then we proceed to the modeling of the mechanical behavior of fabrics. You can see here a two-dimensional representation. In the same sense, we have the third-dimensional representations. You see the application of the forces and the deformation appearing in the lower right corner. Here you can see the modeling of more complicated textile structures like twill or satin. And we have proceeded also to the modeling of knitted structures. That it's a more difficult part because the deformations are really high compared to the woven structures, and this imposes converges problems to the numerical tools. However, we had a considerable success in this modeling. Other structures like interlock, more complicated structures. And in warp knitting as well, we have Sarmer's structure modeled. It's really a big unit cell. You see in the left is the unit cell compared to the plane wave when we have just two yarns interacting. Here you have really a big block of 9 loops interacting. So it's really a very complex unit cell. You can see here the mechanical analysis with the blue elements in the top being the undeformed states, and the white ones are the deformed ones in various directions. And maybe the most complex modeling we had in the three-dimensional textiles, where we had to model the fibers, and after that to model the upper layer, the lower layer, the intermediate layer. And this really led us to the bounds of the method. It was really very much computer consuming and time consuming in order to have such a modeling. So this is the reason we passed in a stepwise modeling. That means we have modeled the unit cell, and after that we have used this unit cell as a part of the macromechanical model, so that we will reduce the computing time. These are the spacer fabrics. You know them well. They are really promising fabrics for many technical applications. Practically, we have two layers up and down and intermediate fibers to connect the upper and lower layer. They are usually produced with warp knitting techniques, that means high-speed techniques, and they have very good properties concerning their permeability, the heat and moisture transfer, that means they are very hygienic and healthy products, and they provide considerable compressional resistance. You have seen maybe these fabrics used as elements for concrete constructions. There may really have many applications in automotive interiors, personal protective equipment, medical textiles, construction, and so on. Of course, an important property on these materials is the viscoelastic behavior. That means very often we are asked to predict their behavior over the time. If we apply a load, what will happen after a certain time? It's not only behavior in one moment as it happens in the usual analysis of the elasticity, but here we have to add the parameter of time, so we pass to the viscoelasticity, and there are not many studies in this field. So we study practically two deformations, which are really almost similar but inverted. We have the application of a load, and we try to predict the deformation, and or to apply deformation and to try to predict the load after a certain time. As the majority of the people working in mechanics know, we have practically, we model practically the viscoelasticity through the Maxwell and Voigt law models. We have chosen a generalized Maxwell model. As you can see, the right side practically is a parallel connection of Maxwell models with a spring on the left side. So we have performed some experiments. We have applied the compressional deformation of 2 millimeters, and then we have to wait 6 minutes to see the relaxation. And we have the relaxation data in order to use for the simulation, in order to evaluate the viscoelastic properties of the structure. When we had this information, we could use the viscoelastic properties in order to create the model and to see what happens in the deformation applied. So we have developed a testing instrument in order to be able to apply the deformation by the vertical rod, and the table, the pressing table, is based on a load sensor, so that we could apply the deformation and measure the load created. And after a certain time, we could see really the load minimizing. That means there was a relaxation of the material. Some technical data about the experiment. So the idea is exactly this one. We have the sample is supported, and we have the probe that is applying the displacement. We have made a two-dimensional axisymmetric analysis, and of course we have observed large displacement effects And this is the thing that creates the computational problems. We have took in account the frictional contact, and this is what we had. We consider in the past the mesomechanical model with yarn bending, high displacement, rotations, and so on. We have the macromechanical model with high finite element distortion, and we try now to see the newest tools, what we can use in order to solve this problem. You can see here that we have the ability to change the finite element, keeping stable their dimension. But you see here, when we have the big deformations, we can change the shape of the finite elements. This was the first approach. This is a new tool to have an adaptive mesh. That means the initial mesh of the model can be changed dynamically over the solution, the numerical solution. When the computer realizes that there is a high deformation, then it can change the dimension in order to face this problem. Here you can see a more impressive solution where you can see that by the deformation of the material, and when we face big deformations, the elements change in number and size, making smaller in the areas when we have big deformation. And you can see this dynamic solution. We start with big elements, and these elements become smaller and smaller upon the increase of the deformation. And here you can see the iterations. We start with a certain size of finite elements, and in this orange vertical lines, you can see the change of the dimensions. Then we have a re-solution. When the force increases in some parts, then the computer realizes that something bad happened, so it makes smaller the size of the finite elements, and it recalculates. So you have here maybe 16 recalculations, something like that. However, the cost is really the high computational effort is really time consuming. It will take a lot of time compared to the simple models. And okay, we in engineering try to make it faster and faster. This is an interesting tool, the adaptive mesh, where the computer by itself realizes that there is a high distortion, so we have to change the mesh. But on the other side, this costs in time. It's a really interesting new tool. I think it's under still development, and we will have for sure in the future better use of it. It is a really promising tool, and it makes our life really easier considerably concerning the high deformation problems. On the other side, we try to find typical finite elements with such geometry so that they will be not too much disturbed during the deformation. And we had really good results also having using this method without recalculation, without remeshing. We have found a really good output. So these are this is a typical curve fitting. The blue line is the experimental one, the steps, and the red line is the calculated one. This is a very interesting picture when you can see exactly visually the relaxation. We deformed the material, and here you can see the red area is the area with the high, the area of the high forces generated. You have the stresses here really increased, and after a time, without any further load added or removed, you can see that slowly after a time, this red area is reduced. That means that the material relaxes. And this is really a very interesting modeling aspect, where you can see the relaxation exactly by the application of the load. You have the relaxation of the material after a certain time. You can see we model the time, and after 6 minutes, we have this decrease of the relaxation. We have used this modeling in a large-scale model. We have a body on a mattress, and we want to see what happens if the body remains there for a longer time. And you know, during sleeping, there is a long application of the load. So we have, this is a very big model, and it was not easy to model it with full reality. Simply, we have a bonded contact between the special fabric and the body. We have frictional contact in the places where friction was created. And you can see here the areas of the application of the load. It's more or less known, you know, the head, the hips, and so on. And we can see that the pressure is applied. The material, the formation of the material reacts, and after a while, you have this relaxation curve. That means that in the beginning, the mattress seems to be very stiff to the body, but slowly the mattress becomes a character of softness. It's more soft after a while. So in order to have an overview, in the past, we were starting from the viscoelastic properties of the yarns. We tried to model the microstructure of the fabric. Imagine how difficult it was to represent exactly computationally the structure of the fabric. Then, in order to pass to the micromechanical analysis, we had to define the contact areas, to set the boundary conditions, to try and to achieve the convergence of the model, and to take in a lot of time. Then we were passing in the mesomechanical model. That means we were considering the unit cell as a typical part of the big model, and we had to solve the large-scale model. This was exactly what happened 10 years ago. 10 years ago, we were using exactly this method. Today, from the experiment, we can take the data. They are directly fed to the mesomechanical model, and then we go to the performance of the large-scale model. That means that the computational tools give us the opportunity from the experiment to pass to a mesomechanical model by considering that we have a material, we don't know exactly its microstructure, but its behavior is this one, what we detect from the experiment. And the computational tools are able to take this mechanical behavior and to build a unit cell that responds to this behavior without knowing what is exactly inside. So this is really a very big change, the numerical analysis tools. So this is exactly the newest situation in the numerical model. We have approached the stress relaxation of spacer fabrics. We have ignored the mechanism that creates its behavior. We have just passed through the experiments, and this data, the experimental data, were imported to the numerical model. Depending on our selections, we can use resources of low requirements. That means we can choose a model that is not time consuming. And finally, the results were pretty good. So I would like to thank you if I have completed my presentation. And I have found a nice picture from an ancient fabric found near Athens, something like 6th century, something like that, BC. 5th century BC. And it seems that our ancestors were very close to our aspects. So thank you very much for your attention, and thank you very much for your invitation. I'm here to for any questions, or if you want, you can contact me by email.
Thank you for your presentation. There is a question.
Savvas, first of all, I really thank you for your being here. I appreciate very much for your support to Ulpas. It was a great contribution last time, and this is also a greater contribution to this Ulpas, the 10th Ulpas. I am really amazed about your work, taking the historical approach and making with the most modern calculations and applying it to a very special topic of interaction between the body and the matrix. I have a question. I believe that must be possible, but what is your opinion? The same approach, I believe, can be applied to this compressive garments or individual garments or individual clothing. What do you think about these? Will you be able to make
Yes. The most, I must tell you, the simplifications we have made here. We considered the body as a rigid body. Unfortunately, it is not a rigid body in reality. It is, compressive. You can see the muscles, and the body behavior is not rigid. So the problem here is that we cannot conduct research by touching the human body. There are some ethical problems. So we could not, I could not be, in an experiment in order to measure the elasticity and the compressional behavior of my arm or my body. This is forbidden. So yes, we could apply this method, but it will take time concerning, especially these ethical, limitations. There are some limitations in every university. You have these ethical committees, and in order to make experiments, but just to touch the body, we need to wait for months and to ask for permissions and so on, and how it will be. And it's really a big mess, and I hope one day we will overcome it. But this is the major problem concerning the contact of fabric to the human body. It's more bureaucratic than technical.
So, thank you very much. I really appreciate it. Thank you.
Thank you very much for your invitation. I'm really happy.
Dear Professor, I have a short question to you. I saw that there is an article published by you. It is on Bitcoin value analysis. Is it right? Is it right?
Is it correct? Yeah, it is correct. It is
okay,
correct.
I want to ask that. Is it time to buy? all salon waiting your answer now.
I must confess that it was an article written by accident. Okay, it will take time to tell you why and so on. However, it is we tried to cross-correlate the value of the Bitcoin with some known values, gas, petroleum, dollar, gold, and so on. And of course, I don't have such a research interest. Simply, it was because of an Erasmus student whose professor died. He came in Athens, the professor disappeared. And I tried to help him. So I was involved in this project just for helping this student. It was not exactly my intention
Okay,
to get
thank you,
engaged with
Professor. Okay, thank you, Professor. Thank you.
You're welcome. Bye. Thank you for inviting me.
Next,
Thank you. Bye.
Symposium. And now we are
Bye-bye.
continue with other online presentation. This presentation will be presented by Harun. I want to introduce him. Harun 2017 yılında Anadolu Üniversitesi Kimya Bölümünden mezun olmuştur. Aynı yıl İspanya Oviedo Üniversitesi'nde stajyer olarak 3 ay çalışmıştır. 2018-2021 yılları arasında Eskişehir Teknik Üniversitesi'nde Analitik Kimya Bilim Dalı'nda yüksek lisans eğitimini tamamlamıştır. 2021 yılından itibaren Eskişehir Osman Gazi Üniversitesi Polimer Bilim ve Teknolojisi dalında doktora eğitimine devam etmektedir. Bugünkü sunum konusu Production of Macroporous Reduced Graphene Oxide Aerogel in Thin Film Form via Electrospinning Technique. Sunumunuza başlayabilirsiniz.
Merhabalar. Sunum görünüyor mu?
Biz sunumunuzu görebiliyoruz. Bir sonraki slayda geçebilir misiniz? Evet, tamam. Sorun yok. Devam edebilirsiniz.
Tamam, teşekkür ederim. Öncelikle merhabalar. Bugün sizlere elektrospinning tekniğiyle ince film formunda büyük gözenekli indirgenmiş grafen oksit aerogel üretimi hakkında kısaca yaptıklarımı anlatacağım ve bilgi vereceğim. Sunum içeriğine bakacak olursak çalışmanın amacı giriş kısmında teknik bilgiler, metodumuz, sonuç ve ileriye yönelik çalışmalarımızı hedeflediğimiz hedeflere yönelik bilgiler şeklinde devam edecek. Bu çalışmada biz makro gözenekli indirgenmiş grafen oksit aerojellerin elektrospinning tekniğiyle ince filmler halinde üretilmesini amaçladık. Bu indirgenmiş grafen oksit aerojelleri üretmek için de bir template'e ihtiyacımız oldu ve bu template olarak da poliakronitril tercih ettik. Kısaca bakacak olursak aerogel nedir diye, aerojeller bir jelin içerisindeki sıvı bileşenin hava ile değiştirilmiş olan katı maddeleri diye kabaca anlatabiliriz. Duman gibi görüntüleri olduğu için bazı kaynaklarda donmuş duman ya da mavi duman diye de adlandırılırlar. Büyük oranda havadan oluşurlar bu malzemeler ve en önemli özellikler arasında da çok hafif, yalıtkan, çok porlu bir yapıya sahip olmaları ve oldukça düşük yoğunluğa sahip olmaları sayılabilir. Örnek verecek olursak mesela burada sol tarafta görmüş olduğunuz fotoğrafta bir alevin üzerinde asılı duran bir aerogel parçası var ve onun üzerinde bir çiçek görmekteyiz. Aerojelin yalıtkanlık özellikleri, yalıtım özelliği sayesinde çiçek alevden korunuyor. Sağ taraftaki fotoğrafta da yine sağlamlık özelliğine bakacak olursak da 2,5 kilogramlık bir tuğla kütlesinin altında sadece 2 gram kütleli bir aerogel parçası ve bunu taşıdığını görmekteyiz. Aerojeller hakkında bize bilgi veren 2 adet fotoğraf burada var. Grafen oksit hakkında da bilgi verecek olursak öncelikle grafen yüksek mekanik, termal ve optik özellikleri sayesinde büyük ilgi gören 2 boyutlu bir karbon malzemedir. Grafenin daha doğrusu çeşitli tekniklerle oksidasyonu yoluyla birçok teknik var bununla alakalı. Yaygın olarak sentezlenen grafenin oksitlenmiş formuna ise grafen oksit denir. Şu ortada görmüş olduğumuz. Bu yapısında gördüğünüz gibi bolca oksijenli gruplar bulundurur. Ve bu da grafen oksitte kimyasal reaktivite, mekanik ve elektronik bazı avantajlar, termal ve optik özelliklerini geliştirmesine imkan sağlar. Bu oksijenli gruplar grafen oksitin kimyasal modifikasyonunu ve daha işlevsel hale gelmesini sağlamakla beraber bu fiziko-kimyasal davranışları da elektrokimyasal olarak ya da kimyasal olarak da ayarlanabilir hale getirir. Son zamanlarda grafenoksitin indirgenmiş grafenoksit, grafenoksitle indirgenmiş grafenoksit daha doğrusu yüzey işlevselliği ve bu saydığım avantajlar sayesinde son derece ilgi görmektedir. Electrospinning tekniğinden de biraz bahsedecek olursak, Electrospinning tekniği kısaca şöyle hemen bir şey göstereyim, işaretleyici. Kısaca görecek olursak buradaki gibi bir şırınga, çözeltiyi vermek için bir pompa ve yüksek voltajlı bir güç kaynağından oluşur kabaca. Ve lifleri toplamak için de elektriksel olarak iletken bir kolektör dediğimiz bir toplayıcıdan meydana gelir. Kabaca bu şekildedir. Sağ tarafta da gerçek cihazın fotoğrafını da görmekteyiz. Bu spinning işlemi sırasında çözücü hızla buharlaştığından dolayı şırıngadan çıkan ipliğin çapı sürekli olarak küçülmektedir ve bu durum ultra ince bir lif oluşumuna sağlar. Daha sonrasında bu yüklü fiber elektrostatik çekim sonucunda bu kolektör üzerinde biriktirilir ve çözeltinin viskoz özelliklerine ve diğer elektrospinning parametrelerine bağlı olarak elde edilen fiberin çapı onlarca nanometreden birkaç mikrometreye kadar geniş aralıkta üretilebilir. Burada elektrospinning tekniğinin tercih edilme sebeplerine bakacak olursak burada gözüktüğü üzere basit bir süreç olması, basit bir proses olması, yüksek gözeneklilik ve kontrol edilebilir bir gözenek yapısına bizi ulaştıran bir yöntem. Ayrıca kontrol edilebilir mikro ve nano boyutlu lifler sağlaması ve malzeme kombinasyonundaki kolaylığı gibi avantajlarından ötürü tercih edilen bir tekniktir. Elektrospinning nanolifleri ise çevre uygulamalarında, savunma sanayide, biyomedikal uygulamalarda, özellikle filtrasyon uygulamalarında oldukça yaygın olarak kullanılır ve bu alanlarda kullanım potansiyeline sahiptir. Bizim yaptığımız metotta, daha doğrusu biz bu spinning tekniğinde bir template ihtiyacımız oldu ve bir template'i poliakronitril tercih ettik. Kısaca PAN diyebiliriz. Bu çalışmada da yüksek gerilme mukavemeti, termal ve mekanik stabilitesi ve solventlere karşı aşınmaya karşı direnci nedeniyle PAN tercih ettik ve bu tür nanolifler tekstil sektöründe, doku ve membran mühendisliğinde bildiğiniz gibi ve biyosensörlerde de kullanım alanı oldukça fazladır. Bizim yaptığımız sentezde, daha doğrusu yöntemimizde ihtiyacımız olan grafen oksiti kendimiz sentezledik. Grafen oksit, grafitin oksidasyonu yoluyla ve modifiye Hammers metodu dediğimiz bir metotla sentezlendi. Burada da senteze ait fotoğrafları görmektesiniz, başlangıç ve bitişi gibi. Gelecek olursak, spinning aşamasına gelecek olursak, öncelikle poliakronitril fiber ve grafen oksit katkılı poliakronitril fiber, yani PAN ve PANGO dediğimiz, kısalttığımız iki farklı fiber atımı yaptık karşılaştırma amacıyla. Bakacak olursak önce 1 gram, yaklaşık 1 gramlık PAN ve 10 mililitre DMF içerisinde 60 santigrat derecede çözdükten sonra içine %5 ağırlıkça %5 oranında grafen oksit kattık ve bu yaklaşık bir gün boyunca, tabii ki içine bir de stabilizör, Twin80 stabilizör eklendi ve homojen bir karışım oluncaya kadar yaklaşık 24 saat boyunca bu karışmaya bırakıldı. Daha sonra ertesi gün bu elektrospinning cihazında atımı yapıldı ve grafen oksit poliakronitril filmler üretildi. Bu üretilen filmler içerisinde tabii belli bir miktarını keserek indirgeme işlemini başlattık. İndirgeme işlemi için de hidrazin hidrat tercih ettik indirgeyici ajan olarak. Ve 95 santigrat derecede bu muamele edildikten sonra, indirgeme işlemi bittikten sonra grafen oksitten, daha doğrusu bu indirgediğimiz grafen oksit PAN filmden template'imiz olan PAN'ı uzaklaştırmak için DMF içerisinde yıkama işlemi gerçekleştirdik. Bu indirgenmiş grafen oksitin aerogel film olarak aerogel üretilmesinde son basamak. ve elde ettiğimiz, burada da fotoğrafında gördüğümüz indirgenmiş grafen oksit film aerogel elde edildi. Burada ürettiğimiz filmleri karakterize etmek için bazı çalışmalar yaptık. Bunlardan biri de SEM görüntüleri. Burada sol tarafta görmüş olduğunuz SEM görüntüsü bizim bir boş dediğimiz, yani sadece poliakronitril attığımız fiberin görüntüsü. Ortadaki görüntüde ise grafen oksit katkılı pan filme ait görüntü. Görüldüğü üzere burada grafen oksit tabakası ince lifler arasında ve liflerin üzerinde gözüküyor, bulunuyor. Ve bu sağ tarafta görmüş olduğumuz görüntüde ise indirgenmiş grafen oksit aerogel filmin çözücüyle, yani DMF ile yıkanması sonucu elde edilen görüntü. Burada gördüğü üzere template'imiz, daha doğrusu template olarak kullandığımız poliakronitril büyük ölçüde uzaklaşmasına rağmen %100'lük bir uzaklaşma söz konusu değil. Her ne kadar liflerin arasındaki mesafe ve pore size'ları büyüse de hala bir miktar template kaldığını buradaki SEM görüntüsünden görmekteyiz. Daha sonra bu filmlerimizin bir de IR sonuçlarını, IR analizlerini gerçekleştirdik. Burada IR analizleri sonuçları da bir önceki SEM görüntülerini destekler nitelikte sonuçlar. Burada mavi renkte olan pan filme ait, boş filme ait yani IR spektrumu. Burada gördüğünüz gibi 3400-3600 değerleri arasında normalde hidroksi grubuna ait, yani yapıdaki karbon OH piki bulunmakta. Gördüğünüz gibi aşağıda grafen oksitten kaynaklı bu pikler gözükmekteyken panda bu pikler gözükmemekte. Böyle bir pik yok yani. Daha sonra burada gösterilen panın yapısında bulunan C üçlü bağ N piki, yani yaklaşık 2240 ve 1450'de görülmektedir civarında. Ancak görüldüğü gibi piklerin şiddetinde panın uzaklaştırmaya çalıştığımız, yani burada kırmızıyla gösterilen indirgenmiş grafen oksit aerogelde pik şiddeti azalmasına rağmen tamamen yok olmamıştır. Bu da bize bir önceki görüntülerde de dediğimiz gibi sentez modifikasyonumuzun başarılı olduğunu, fakat template uzaklaştırma konusunda yüksek performans için biraz daha uğraşmamız gerektiğini göstermektedir. Tabii daha biz bu aşamada, yani bu sentez yönteminde biraz daha yolun başındayız. Ama bununla ilgili çalışmalarımız da devam ediyor. Sonuç olarak bakacak olursak biz bu çalışmada ne gibi sonuçlar elde ettik diye bir bakacak olursak poliaklonitril, grafen oksit katkılı poliaklonitril ve indirgenmiş grafen oksit aerogel Electrospinning tekniğiyle başarıyla sentezlendi. Pan şablonunda, yani pan template'inde ince film yapılı grafen oksit aerogeli üretim açısından farklı bir bakış açısı kazandırmış olduk. Ki bizim burada vurgulamak istediğimiz zaten asıl noktada burası. Aerojeller çok yeni materyaller, çok yeni teknolojiler değil. Tabii nispeten yeni ama bu ince film yapısında, yani bir spinning tekniğiyle bir yere atılarak çok ince bir yüzeyi kaplama ya da yüzeyde oluşturma gibi üretmek ve template'de bu spinning tekniğini kullanmak nispeten yeni bir bakış açısı. Yapısal olarak bu ince filmler şeklinde olduğu için çok fazla biyomedikal mühendisliği uygulamalarında, biyosensörlerde umut verici bir çalışma olarak değerlendirebiliriz. Tabii ki dediğim gibi yolun başındayız. Daha farklı, daha değişik yaklaşımlarla bu konuyu geliştirmek amacımız. İleriye yönelik yapmak istediğimiz çalışmalara baktığımızda da aklımızdaki ve yapacağımız çalışmalar öncelikle farklı bir template ile, farklı hidrofobik ya da hidrofobik olabilir. Kendi ürettiğimiz belki de bir polimerle yine bu grafen oksit aerojeli üretmeyi amaçlıyoruz. Farklı template'lerle denemeyi. Daha sonra indirgeyici ajan olarak da biz burada mesela hidrazin hidrati tercih ettik. Farklı indirgeyici ajanlarla farklı performans iyileştirmelerine veya biyomedikal uygulamalar için uygunluğa gidilebilir. Farklı indirgeyici ajanların performansı denenebilir. Farklı template'lerde yine. Son olarak da bu ince film aerojellerin adsorban, taşıyıcı sistemde ya da sensör gibi, biyosensör gibi özellikle kullanımları tabii ki optimizasyon çalışmaları yapıldıktan sonra denenebilir, test edilebilir. Bizim de amacımız bunu daha da geliştirmek ve bu yolda ilerlemek. Şimdilik anlatacaklarım bu kadar. Beni dinlediğiniz için teşekkür ederim. Sağ olun. Biraz hızlı oldu sanırım.
Yok, gayet vaktinde bir sunum yaptınız. Teşekkür ediyoruz sunumunuz için de. Sorumuz var mıydı? Salondan sorular var. Onları alacağız. Hocam buyurun.
Merhabalar. Öncelikle teşekkürler Harun Bey. İlk öncelikle şunu sorayım. Pan polimerini uzaklaştırmışsınız. H ederek. Buradaki kütle kaybını hesapladınız mı acaba?
Bizim şu anda bu proseste odaklandığımız nokta aslında yani SEM analizleriyle ve IR analizleriyle tamamen panı %100 bir şekilde uzaklaştırmaya yoğunlaştık. Eğer %100 şekilde uzaklaştırmayı yani uzaklaştırdığımızı yaptığımızda, fark ettiğimizde ya da başardığımızda ondan sonra bu dediğiniz gibi hesaplama kısımlarına geçeceğiz. Ama şu anda dediğiniz bir hesaplama kısmına henüz geçmedik.
Ya bu basit bir şekilde %5 grafen oksit koymuşsunuz. Tamamen panı uzaklaştırıldığında %95'ten daha fazla bir miktarda kütle kaybı olması lazım. Bunun IMF, oradaki nanolif yapının çözülmesi öncesi ve sonrasında basit bir ağırlık hesabıyla yapılabilir. Ya burada gördüğüm kadarıyla burada yüksek miktarda pan hala yapının içerisinde duruyor. Zaten %5 gibi bir grafen oksit ilavesiyle o bir backbone oluşturarak normal şartlarda hani amaç aerogelde tamamen polimerin uzaklaştırılıp oradaki grafen oksitin grafene çevrilip orada bir backbone oluşturarak birbirine tutunması. Ya bir tavsiye olarak burada hani ilave olarak denilebilir. Farklı grafen oksit konsantrasyonlarına denilebilir. %5 küçük bir oran. Bu daha yüksek oranlara çıkılarak daha kolay bir grafen oksit plakalarının birbiriyle tutunması. Bu sayede daha başarılı bir aerojele giden bir yapı diyeyim. Onu elde edebilirsiniz. Şu anki oran çok düşük. Yapıdaki panı uzaklaştırdığınız takdirde tamamen bu hani stabil bir film halinde kalmayacağını ben öngörüyorum. O yüzden biraz daha yüksek grafen oksit katkılarına çıkabilirsiniz. Bir de o basit bir ağırlık hesabıyla da panın yüzde ne kadarını uzaklaştırdığınız hakkında fikir sahibi olabilirsiniz.
Teşekkür ederim. Biz değişik konsantrasyonlarda aslında grafen oksit katkısı denedik fakat şöyle bir sonuçla karşılaştık. Daha doğrusu sorunla diyelim. Bu spinning dağıttığımız zaman biraz fazla yani belki de daha uzun süre muamele etmek mi veya farklı tekniklerle muamele etmek mi gerekiyor onu tam emin değilim ama tıkanmalar meydana geldi spinning ucunda atarken. Biz de biraz daha düşürelim ve %5'te güzel bir atım, güzel homojen bir atım olduğu için %5'e kadar indirdik. Yani dediğim gibi aklımızda yapacağımız sizin söylediğiniz kısımlar çalışmalar. Daha komplike çalışmalar.
Gördüğüm kadarıyla solüsyonu hazırlarken yani karıştırma yöntemiyle hazırlamışsınız.
Evet.
Propsonikatörden bahsetmediniz, göremedim. Eğer hani propsonikatör kullanırsanız daha yüksek oranlarda dağıtım grafen oksitin dağılmasını sağlayabilirsiniz.
Teşekkür ederim, sağ olun.
Başka soru var mıydı acaba? Tekrardan teşekkür ediyoruz ve
Ben teşekkür ederim, sağ olun.
bir sonraki sunumumuz on-site olacak. Sunumu yapacak kişi Merve Nur Sağırlı. Kısaca kendisinin özgeçmişinden bahsediyorum. Lisans ve yüksek lisans eğitimini İstanbul Teknik Üniversitesi Tekstil Mühendisliği bölümünde yapmıştır. 2016 yılından beri İTÜ-TEMAK Laboratuvarı'nın ailesinin bir parçasıdır. Nanoliflerin üretim ve karakterizasyonu üzerine çalışmaktadır. Günümüzde de Aerogel Teknolojileri Limited şirketinin Ar-Ge mühendisi olarak görev yapmaktadır. Buyurun sunumunuzu gerçekleştirebilirsiniz.
Hello. Dear audience, welcome to 10th of International Fiber and Polymer Research Symposium. I am Merve Nur Sağırlı, graduate student of Textile Engineering. I will make a presentation on effect of solvent ratio on spinnability of solution-blown PVDF nanofibers. In this presentation, first of all, I will start with nanofibers, properties of nanofibers. Why are we trying to produce them? And then nanofiber production methods. After that, I will talk about our experimental studies, about production of PVDF nanofibers and the evaluation of their spinnability. Then I will summarize a conclusion about this work. Nanofibers are the fibers having average fiber diameter less than 1 micrometer. And they have 3D porous structures, so this gives most of advantages in the most of areas. And they have high specific surface area. This gives, especially for filtration applications, this is what we are looking for, because we are trying to capture the particles and they need to find a high area to be captured. And nanofibers have slip flow on their surface. This is again, especially for air filtration applications, this is an advantage to reduce the pressure drop, but we are trying to avoid. So how are we producing these nanofibers? We have 3 common methods for this. These 3 methods are based on production of nanofibers from polymer solution, and we are trying to having fibers from the solutions by surpassing the surface tension of them. So we have 3 main systems like electrospinning, solution blowing, and centrifugal spinning. These are named as according to the force that is surpassing the surface tension. So in the electrospinning system, we have electrical forces. Solution blowing system, we have pressurized air for that. And for centrifugal spinning system, we have centrifugal forces that is surpassing the solution surface tension. And when we compare these 3 systems, we have production rates especially very low on electrospinning and higher in both solution blowing and centrifugal spinning systems. In this study, we choose centrifugal solution blowing system because of its safety and high production rate. We used Aerogel aerospinner for the solution blowing production, and our production parameters are, in nanofiber production, we have material parameters and production parameters. So as material parameters, we try to see effect of solvent ratio on product spinnability of polymers. And as a production parameter, we chose compressed air. We have 5 different solvent ratio, and we have 3 different air pressure values here. We have polymer as polyvinylidene fluoride, which has most of advantageous properties according to its physical, chemical, and electrical properties. And we has 12 weight % as solution concentration, and the nozzle collector distance and duration were same constant in this study. Generally, in the production parameters, we have feed rate for such systems, but in the nozzle geometry we use, the solution is fed by air pressure, and its feed rate according to the air pressure is shown in this graph. And I will talk about what we have after our production trial. So these are our SEM images of the fibers we obtained. As you see here, we have lots of droplets, beads, and bundled structures here. In order to have an optimum value of spinnable fibers from polyvinylidene fluoride, we had a criteria table. Sorry, I was trying to go to the previous slide. So we had a criteria table. This table is so we chose these values in this tables according to our previous studies. For example, in the nanofibers, when we saw beads, droplets, or bundle structures, we can say that this is not spinnable or has lower spinnability. So when we have, for example, in a chosen area, when we have beads, droplets, more than half of that area, this is ineffectual according to spinnability. And when we have 1% of that area as beads or droplets, we chose it as effectual spinnable value. And it is also the same for bundles, fiber bundles. When we have more than half fibers as bundle structures, it was ineffectual. And when we have less than 100%, it is effectual. And according to third criteria, it was fiber diameter. We are trying to go to submicron fiber diameter. So in order to choose ineffectual value, we said that if it has more than 1 micrometer diameter, it will be ineffectual, and if it has less than 100 nanometer diameter, it will be effectual or spinnable value. Here, in these green boxes, the grades of spinnability are shown. So we have highest grades as spinnability as 3, and we have it in 8 different samples. When we look into graphs, we can choose the most optimum one. Well, here we have 2 graphs for our 3 criteria. And first one shows the first and second criteria, like the effects on nanofibers. One of them is area of beads or droplets, and the other one, the count of fiber bundles. And the second graph shows us fiber diameters. When we look at the first graph, when we increase the amount of DMF in the solvent, we have beads or droplets higher. And when we have acetone in our solvent, we have bundles as higher, because in the sample produced by fully DMF solution, they have lower bundles when we look at the bundle graph, and we have higher bundles in the solutions produced samples with the fully acetone fibers. This is caused by, for example, the beads or droplets are caused by surface tension of the solvent. When the solvent surface tension is higher, we cannot have the regular jet structure, so it goes to the collector as bundles or droplets. Here we have higher surface tension in DMF according to acetone, so we have higher beads or droplets in the DMF. According to bundle structures, it is affected by the solution viscosity. For example, if we have lowest viscosity solution, it gives some instabilities like bundles or branch structures in the fibers. So we have fiber bundles when we have higher acetone, because acetone lowered our solution viscosity. When we look at the fiber diameter, we have lower fiber diameters when we increase the DMF amount. This is caused by pressure vapor of solvent. When we have higher pressure vapor solvent, it gives viscose resistance. Yes, viscose resistance to our polymer jet. So and acetone has higher vapor pressure compared to DMF, so it gives a higher fiber diameter result. Here also, since we have bundled structures in acetone samples, we have some fibers higher than one micrometer, and in DMF we have fibers, average fiber diameters, less than 500 nanometers. When we compare these results and look at our grades, we saw that the solvent having 30/70 acetone DMF ratio were better results according to the spinnability, and the pressure value was 3 bars. So when we go to conclusions, so in conclusion, when we have the more amount of acetone in solvent, it gave more clogging of nozzle. I forgot to say that the previous graphs didn't having some regular structure, so that was caused by the clogging in the nozzle. When we have higher acetone ratio, it gave more clogging, but when we have higher DMF ratio, the clogging problem reduced. And in the solvent system, increasing acetone amount increased fiber bundle, and increasing DMF amount increased the beads or droplets in fibers, and also increasing DMF amount decreased the fiber diameter. These are references in this presentation, and thank you very much for listening.
Biz de sunumun için teşekkür ederiz. Tamamdır hocam. Soru var mıydı acaba salondan? Bir sorumuz var. O zaman benim bir sorum var. Which is the optimum?
Optimum one was optimum one was 30 to 70 acetone DMF. No. 30 to 70 DMF. And 3 bars.
Now we will listen to sponsored presentation Oxide Acrylic.
Hello everyone, and thank you for giving this opportunity to us on behalf of my company and myself. My name is Saras. I'm a textile engineer. I was studied in Istanbul Technical University and just received my PhD degree last year in textile engineering again. Today I will talk about our company AXA in brief. What we are doing, who is AXA. I will talk about this a little bit. Before going into detail, I would like to talk about our holding company, Akkök, in brief. Akkök is operating in 5 main branches. These are chemicals, real estate, energy, services, and textile. AXA is located under the branch of chemicals with its sister company, Dovax and Akim, which is located in the same zone in yellow. Here is the general view of our plant. there are three main zones, we can say, and also one additional zone. These are the first, the chemical part, which is including raw material storage, polymerization, distillation, fiber spinning. And with the part which you can see with the green part is the textile part, which we are converting our fiber to different forms, like a staple fiber, stretch for tops. In some cases, we are dyeing and so on. And also we are having our own energy plants to produce our own electricity and steam, which is used in the production. And lastly, the last operation is a port operation, which we are receiving our raw materials for the production. If we briefly look at the history of AXA, last year was the 50th anniversary of AXA in production. AXA was established in 1968 with a license agreement. The first own process development was made in 1977. Then, starting from the beginning of the 21st century, product development studies has been started. The first product that was developed was solution-dyed acrylic fiber, which is used in outdoor applications. And since that time, it's growing very fast. And one of the major developments in AXA was carbon fiber development, which started in 2006. And after it's developed, for some time, it was operated by AXA itself, but in 2012, AXA and Dow Chemicals made a joint venture, and it's separated as a separate company called Dow AXA. And the R&D center has been established in 2017. Since that time, we are making lots of process and product developments. I will talk about them a little bit. If you look at the market share of AXA, we are having 25% market share all over the world in acrylic fiber markets. Turkey is the second biggest acrylic fiber market in the world, and we are having a 75% share in Turkey. And when we talk about outdoor acrylic fibers, it's basically solution-dyed acrylic fibers. We are having more than 70% market share. And when we briefly look at the properties of acrylic fiber, these are very, let's say, common properties that can easily be found from the literature. Easy washable, resistant to chemicals and sunlight, wool-like appearance, and dyeability are the major properties that we can show. And by the effect of these properties, it can be used in a variety of applications, like as knitwear, upholstery, hand knitting, carpet, filtration, fake hair, friction materials, and so on. And now let's look at 20 years back, more or less, in 2000. These dots show the number of or the locations of acrylic fiber that the acrylic fiber producers, let's say. It was much more common compared to today. Total acrylic fiber production at that time was 2.7 million tons. And AXA was having 250,000 tons at that time. Then we come to, let's say, today, the acrylic fiber decreased to 2 million tons, whereas AXA has increased the capacity. And lastly, today, acrylic fiber market is like 1.3 million tons, whereas AXA is having the capacity 350,000 tons per year. So, as you can see, total fiber market has doubled since 20 years, let's say. In the same time, acrylic fiber market, let's say, came to half of the market with which it was in 2000. But AXA is increasing its capacity since that time. So how it happens, I will talk about it a little bit during this presentation. So if you look at our R&D strategy, we are four main topics. These are new technologies, which means the technologies that's not existing in AXA at the moment, but we are developing, let's say. Sustainability, most of the presentations touch the sustainability point, so inevitably we are dealing with sustainability topics. New fibers and polymers means the new fibers and polymers that we can produce with the existing plant, let's say. And a know-how project, it shouldn't be, let's say, linked to a commercial product. It's just to increase or let's increase our expertise and know-how, let's say. So I will start from the bottom to top. From the know-how project. What are main topics for know-how projects? Let's look at this. The first one is polymerization methods. Our R&D team is studying on different polymerization methods to check for the opportunities to improve the properties of existing polymers, or even produce new polymers for different type of applications. The second topic is modification techniques, such as structural modification. It can be surface modification. It can be some, let's say, functional modification, and so on. And for sure, we are working on fiber spinning technologies. Today, our production technique is wet spinning technique, but we are also checking for different fiber spinning technologies. And for sure, the green chemistry is one of the most important topics, like green solvents, green chemicals, green additives, and so on. When we come to new polymers, new fiber and polymers, what we are having? As I mentioned, the first product that we have produced was the solution dyed acrylic fiber. The most important property of this fiber is it's UV resistant. Our customers are giving 10 years warranty to its customers for the color retention so we need to ensure that we are giving this property. So we are always working on this topic. So now we are having let's say patent application which we improve the UV resistance property of acrylic fiber, and to ensure that we can give these high years of warranty for the solution dyed acrylic fiber. Another important property of these fibers is its abrasion resistance. In order to improve the abrasion resistant property of acrylic fiber, let's say, we are also having a patent application with a modified wet spinning technique, let's say. And as you can see from the graph, now we are having a 40% increase compared to, let's say, regular staple acrylic fiber. Another development is solution dyed acrylic filament yarn. The history of this product dates back to 1950s maybe, but the solution dyed version is just produced by AXA and it's patented. And what it brings to us brings higher tenacity and also higher abrasion resistance. It's again used in outdoor applications. As you can see from the improved abrasion resistant staple fiber to filament yarn, we are having a 60% increase in the abrasion resistance. So especially for the outdoor furniture applications, it's one of the crucial points. As we are having filament yarn, we are also working on texturizing of the filament yarn, which was my major topic, let's say. And also another product that we are developing is antimicrobial acrylic fiber. This property is given by the, let's say, by some additives, so it's inherent and having a permanent effect. Even it's blended with some other fibers which are not antimicrobial, it can show antimicrobial property. Another one is modacrylic fiber, which is one of the newest developments of AXA. It's again the chemical part, the polymerization part is again patented by AXA. One of the important developments with monoacrylic fiber, solution dyed monoacrylic fiber, it's just only can be used produced by AXA today. So what it brings to us, it brings permanent colors after several washing cycles at elevated temperatures, color retention after sunlight exposure, and less water consumption up to 92%. And let's look at the sustainability topics. We are having two commercial products at the moment. One is recycled acrylic fiber. AXA is the first producer of this fiber. And on the right hand side, you can see eco-friendly dye acrylic fiber. Both are having less water consumption and also less carbon emission. And the more important part is the traceability of these products, because as you ensure that you are using a recycled acrylic fiber or eco-friendly dyed acrylic fiber, so you need to give this traceability property as well. So we are using some additives to give this traceability property. And as you can see, with a very basic instrument, these fibers can be detected by the end users, we can say. Inofilis is another product which is a fake Angora, alpaca, and mohair-like acrylic fiber. These are separate fibers. These are developed according to, let's say, actual, let's say, alpaca, mohair fibers, I can say. And what else we are having? We are also working on bio-based materials, biodegradable products, antimony-free monoacrylic fiber. It's one of the important points. Monoacrylic fiber is using antimony pentoxide to enhance the flame retardancy property. We are working on an antimony-free version, which will be a, let's say, destructive development if we can succeed. And also upcycling is another interesting point for us. What does upcycling means? After the, let's say, lifetime of a particular material ends, you convert it to another material which can be used for some other applications. So AXA is also working on such topics, let's say. If we can sum, so we believe in the, let's say, circular economy. Here you can see, today we are using a fossil-based raw material, it's acrylonitrile, but we are trying to replace it with a bio-based raw material. And we are also recycling our production waste and make it again an acrylic fiber. And by the biodegradable versions or the upcycling methods, we are planning to convert our waste finished product made of acrylic fiber again to bio-based raw material or convert to another fiber, another material which can be used for some other applications. Oops. When we look at the new technologies, as I mentioned, these are the ones that cannot be produced with our existing machinery and so on. We are also developing some new technologies inside and also making some technology transfers. One of the most important developments within this year is ultra-molecular weight polyethylene. Today is in the pilot stage. Until the end of this year, we are planning to have the approved material in hand. And if we do so, we will take a decision to make an investment for the ultramolecular weight polyethylene. It's totally separate from our ongoing business actually, but as we are dealing with the new technologies, we are making such products. And super acrylics, it's one of the another interesting projects. When we say super in fiber, it means the tenacity. We are talking about the fibers having exceptional tenacity, heat resistance, and so on. So we are trying to develop a super acrylic, both with polymerization and also fiber spinning technique, the combination of these both technologies. So it's still in the R&D stage. Monoacrylic filament yarn. As we are having monoacrylic fiber production technology and also filament yarn technology, we are trying to combine these both technologies. When we commercialize this product, AXA will be the only producer of this product. It will be a value-added product, we can say, for the protective clothing applications most commonly. We are also working on cellulose-based fibers. This means we are trying to find some cellulose-based materials to spin it through our existing spinning lines, we can say. And new FR fibers, as we are existing in the FR business with monoacrylic fiber, we are also trying to develop some new flame retardant fibers. If you look at the flame retardant fibers pyramid, there are, let's say, 3 segments. The upper part is the ones with higher performance and higher cost, and with lower consumption, let's say. These are PBI, PBO, carbon fiber. On the middle layer, there are aramides and FR viscose, and the bottom part is mainly treated cotton. With monoacrylic fiber, today we are in the middle of the bottom and the mid layer. We are covering this part, we can say. And with the new FR fiber, which is still in the pilot stage, we can say, we are planning to obtain, let's say, more flame resistant fiber. There are 3 patent applications for this fiber today, and we are awaiting for the results of this. And lastly, we are also investing to startup companies which are related to our businesses. There are 2 of them. One is Porima, which is producing filaments for 3D printers. And the second one is Iltema, is producing heating fabrics. Before I finish my words, I would like to share our corporate video with you. Thank you for your attention.
Thank you for your presentation. I want to give a small gift to you.
Thank you.
Now we will continue oral presentation will be presented by Andinet Kumella Eticha. You can make your presentation. And I want to introduce Andinet Kumella Eticha to you. Andinet Kumella Eticha is Ethiopian PhD student at Karabük University. He graduated in 2011 and 2014 Bachelor Science and Master Science degree respectively from Addis Ababa University of Technology. Now he is working on biodegradable nanofibers for air filtration applications in Tebak Laboratory. Okay, Andinet, you can start your presentation.
Thank you very much. I hope my Thank you very much. Okay. My name is Andinet Kumella. It's already explained. So I would like to thank all of the researchers who are participated in this research work with the title Electrical Assisted Solution Blowing Spinning of PVDF TPU nanofibers mats for air filtration applications. My presentation outline it starts with introduction, and I'll go step by step until the conclusion. So before I start, I want to say 2 points on the motivation behind this, performing this air filtration till today, because there are many researches which are done, still which are ongoing. So the first question that has come to my mind is that what is the reason for doing this air filtration application till today? And I started looking current age literatures, 2 literatures, which are published as they define there. So here the air pollution, as you can see here, is a major problem still today. So one thing that come to my mind is that we have to focus on ultra thin nanofibers. So we try to a little bit lower to like 300 nanometers of aerosols. So these are the air pollution still today is the major concern for the world. So that we are trying to alleviate this issue. So commercially, there are mainly glass fiber type and HEPA filters. Of course, there is an Ulpas as well. But as you can see here, the filtration efficiency is maximum. Still, researchers are focusing on polymers to produce a high filtration efficiency nanofiber to filter the fine aerosols. So because of that reason, mostly polyvinylidene fluoride has become one of the popular material to be used. And the reason for this issue is that it has a high mechanical strength, good thermal stability, and excellent chemical resistance, but it is poor. Its brittle nature will make it poor for the air filtration application. So to subdue this concern, we are trying to blend it with thermoplastic polyurethanes. So thermoplastic polyurethane has a characteristics features of elasticity. So because of that reason, we try to merge this TPU with PVDF. So our objective is to optimize a PVDF TPU sample having a higher filtration efficiency and better elongation for air filtration application. So this is the sample that we are preparing according to the solutions defined with the table. And this is the method, a schematic drawing of electrical assisted. We make the electrical assisted to improve the spinnability and to reduce the fiber diameter so that we can get the ultra thin fibers which assist us for reducing the aerosols or the problem caused by these ultra thin aerosols. So we try to characterize the morphology and fiber diameter of the nanofiber mats with same analysis, and the filtration efficiency and pressure drop by this air filter test, and the mechanical properties we try to see later on. We try to test the tensile strength of the samples. And I want to here highlight a little bit. So as you can see here, this is a pure TPU. And for all of the samples, there are beads were observed. And the beads the presence of these beads might be the turbulence of the air that we use, that 3 bars. And as we observed here, relatively this 3 PVDF and TPU value, it has a good surface uniformity with lower surface roughness. But for others, there are beads observed and also droplets are considered. And the other thing is, if we look at, for example, this one is pure PVDF, and it is fiber diameter is, as you can see, it is 160. However, if we move up a little bit, it is a 600. And then here as well, 500 and 600, which is their frequency and their fiber diameter increase with the addition of TPU on pure PVDF. And the other, this is the smaller fiber diameter. This is the thinner fibers, pure PVDF. The thicker one is pure TPU, but the TPU has an effect on the fiber diameter. So for example, here, when we decrease or when we add, for example, 75% of TPU on PVDF, the fiber diameter will be improved by 54% as compared with that of pure PVDF. And when we go to the filtration test, here the PVDF has a higher filtration efficiency because of lower fiber diameter, and the TPU have a higher filtration, a lower filtration efficiency with a higher pressure drop due to the diameter effect and other morphological issues. But when we increase when we go from right to left side, addition of TPU will increase the fiber diameter, and we observe it through the morphology. In the filtration analysis, the filtration efficiency of the sample will get dropped. In other words, there will be a higher drag force across the surface of the nanofiber. That is why the pressure drop will get rise. And the other determining factor is the Knudsen number. We calculate the Knudsen number numerically, and it is on the range of 0.74 to 1.24, so that there will be a free flow of air that goes through the air filter, so that the quality factor here as well depends on the efficiency and pressure drop. So as the pressure drop rises, the quality factors will get decreased. So this is what our test result shows. And also this PVDF is higher filtration efficiency. So it is Knudsen number is maximum, because Knudsen number depends on fiber diameter, and the diameter of this pure PVDF is minimum. And it goes like that. On the mechanical properties, as it's shown that TPU have a higher flexibility as compared to PVDF. PVDF is brittle in nature, so that when the maximum force is applied for TPU with 1.4, and the minimum is for PVDF. So we need a sample which have a higher air filtration efficiency with a lower pressure drop and with a higher flexibility in nature. So the addition of TPU, which indicate that the flexibility of the material is improved. So as you can see here, 25% addition of TPU on pure PVDF increase the filtration, the flexibility of pure PVDF by 181%. So as a conclusion, this method is suitable for fabricating ultra fine fibers. I'm sorry. This method is suitable for fabricating ultra fine fibers of nanoscale size aerosols. So with the thinner nanofibers of 105 and with the thicker nanofibers of 176. And the additions of TPU improve the flexibility of pure PVDF. However, it decreases the filtration efficiency. And the optimized sample we select from this study is that 75% PVDF and 25% TPU. It has a closer filtration efficiency toward this pure PVDF, and also it has a higher flexibility toward this TPU value. And finally, it was observed that this high air filtration efficiency of nanofiber was obtained through the electrically assisted solution blowing, but when we observe the pressure drop value, it gets higher. So it is already known that pressure drop has a significant effect on the service life of the fibers and the energy consumption. So even though the samples succeed, but we still have to decrease the pressure drop value so that we set our future work on decreasing the pressure drop of electrically assisted solution blowing for PVDF TPU. Thank you for your attention.
Thank you for your presentation. Is there any question?
Sorry. Make it the no. We are making electrical assistor. For example, if we to decrease the fiber diameter, it makes high listen. Absolutely. I was doing on gelatin nanofibers for electrical assistor for 20. No. I didn't quite know the percentage. I didn't calculate it, but it decreased the fiber diameter. That's why we make electrical assisted. If we do solution blowing only, the driving load is only air, so we cannot find ultra thin fibers at the end. Thank you.
Okay, I want to give your certificate. Now, this next presentation will be online, presented by Ahmad Hivechi. Ahmad Hivechi, are you here?
Yes, I'm here.
Okay, firstly, I want to introduce you. Dr. Ahmad Hivechi is a postdoctoral researcher at Martin Luther University. His research focuses on biomaterial-based nanofibers for tissue engineering and drug delivery applications. He is currently working on the morphology effect of nanofiber scaffolds for advanced ocular drug delivery purposes. You can start your presentation, Dr. Ahmed.
Yeah, thank you for your time. I'm going to share my my screen here. So yeah. Okay. First of all, I would like to thank the organizing committee for accepting my paper for presentation in 10th Polymer and Fiber Research Symposium. My research will be investigating morphology effect of PC nanofiber scaffolds and wound healing rate. And this work is a collaborative work at Iran University of Medical Sciences, Ege University, and Amir Kabir University of Technology. My presentation will include 4 sections. The first section will be introduction, then I will go through experimental, then results will be presented, and then I will go through conclusion. As you know, every year many people lose their organs or they damage their organs through many accidents such as fire, car accidents, and illnesses and other things. So in traditional medicine, the damaged tissue was replaced by another organ by a donor. These strategies had several drawbacks like limited number of donors, tissue compatibility limitation, and low surgery success rate and high costs. So engineers and medical scientists mix their knowledges to built a new branch of science called tissue engineering. This branch offers the possibility to create completely natural tissue and replace failing organ. So what's the strategy? We usually take the cells from the patient, then we expand them on laboratory condition, and then we build a scaffold, which is very similar to the damaged organ with similar chemical characteristics, mechanical characteristics, and other things. So the cell will be located on the scaffold, and they will be transferred into the human body and in the damaged organ. And after a while, the organ will be replaced by the patient. In this field, nanofibers are a very interesting topic because of many reasons, such as high specific surface area, morphological similarity to many other organs like wounds, like other things, and reproducibility of the electrospinning process, exceptional mechanical stability, and wide range of biomaterial that can be electrospun into nanofibers. Nanofiber research to now, we had a very lots of research. Of them was focused on optimizing the electrospinning condition, combining several biomaterial electrospinning process, introducing new nanofiber structures such as core shell, hybrid, and etc., or adding active agents like pharmaceutics, genes, and other things to create a special characteristics to the nanofibers. But there is a but here, because most of them are somehow we lack a little. I mean, to date, we haven't had any research on the morphology effect. As you know, recently scientists have noticed that morphology has a very significant effect on tissue regeneration. And if we signal cells to move and proliferate in a direction so we can heal the wound, the damaged organ, or other things in a faster way. So in this research, we are going to investigate the morphology effect of PCL nanofibers to see how it could happen in wounds. As you know, when a wound happens, the wound will be something like this, and the wound area will be such as this thing. So what happens after a while? Wounds wants to heal itself from here and here. So if we could accelerate the healing rate at this and this direction, so we could heal the wound in a faster way. So what we had in our mind is that we could signal cells in the direction of the center of the nanofibers. So in this research, we are going to present a novel nanofiber structure named as radially aligned nanofibers that could be used for wound healing applications. And we want to compare it with other kind of morphology like random morphology and unidirectional morphology. Let's go through experimental section and see how we did our experiments. In the first section, in the first step, we mixed PCN and acetic acid 90% with 15% concentration on a magnetic sphere for 5 hours. Then this solution was transferred into a syringe, and then electrospinning process performed using a high voltage on a flat aluminum foil to create the random morphology. So let's go through radially aligned and unidirectionally aligned morphology. In the unidirectionally, we had a rotating cylinder, and then the solution will be electrospun on this rotating solution. So we'll have the unidirectionally aligned morphology. But in the radially aligned morphology, we had a flat wooden surface and a metal ring with metal point in the center. So the morphology in this kind of collector will be something like this, and the alignment will be like this. So after this, we started our instrumental analysis. We performed scanning electron microscopy to study the morphology of the nanofibers. We collected the Fourier transform infrared spectroscopy to see the chemical structure of the nanofibers. And then differential scanning colorimetry was performed to see the thermal behavior of the nanofibers. The X-ray diffraction was studied to see the crystallinity of the nanofibers and see if the electrospinning process had any significant effect on their properties. Biological studies was included like tests like MTT assay for biocompatibility studies. In this study, we used L929 cell line and the standard cell culture process. I'm not going to present this because it's very time consuming, so I will go through the other sections. The cell culture was performed on the nanofibers, and then the SEM images was collected. In this, first nanofibers were sterilized and cells were seeded on nanofibers, then incubated for at 37 degrees centigrade for 2 days, and then cells were fixed using glutaraldehyde solution for overnight, and SEM images were collected to see how cells are attached to the nanofiber surface. Let's go through our results and discussion. As you can see here, we are showing the radially aligned nanofiber, and this is the collector we designed in our lab. As you can see, I'm going to zoom into different sections of this nanofiber morphology. So if we zoom here, you can see the tip of the metal point is here, and this is the nanofibers collected on the ring. And the important part is here that you can see the alignment through the the alignment through the radius of this circle is very uniform. So as you can see, we have successfully produced our radially aligned nanofibers. I want to zoom more to the other sections. This is the point. As you can see here, this is here. And this is the nanofibers at here. And this is the nanofiber alignment through the radius of this circle. Here you can see the random nanofibers. Here unidirectionally aligned nanofibers. And here you can see radially aligned nanofiber. We measure the diameter of nanofibers, and the average nanofiber diameter for random nanofibers were 2040 nanometer. For unidirectionally, it was 2057 nanometer, and for radially, it's 226 nanometer here. So we can say that there is a very significant effect on the diameter of the nanofibers. We have the same diameter for all samples, but we have a different morphology. To see the effect of the electrospinning process on chemical properties of nanofibers, we performed a FTIR spectroscopy to see if electrospinning process affects the chemical structure. So all the samples showed the similar spectrum, so we can say that none of electrospinning process doesn't have any significant effect on the chemical property. As you can see here, peaks at 2947 and 2866 are related to CH sp3. Peak at 1730 relates to CO stretch ester. Peak at 1468 relates to CH2 bending OOP. 1365 shows the CH3 bending out of plane. 1294 relates to CO and CC stretch in crystalline phase of the PCl polymer. 1240 shows the COC stretch asymmetric, and 1174 shows COC stretch symmetric. So in the next section, we went through the XRD investigations to see if the electrospinning process had any significant effect on the crystallinity of the nanofibers. As you can see, all samples showed the similar pattern with peaks at 25.2 degree and 23.6 degree. But if we zoom into this region, you can see that the peaks are a little different. And if we use this equation here, which is peak ratio, this peak ratio shows a number that we can compare the crystallinity of the nanofibers. So this peak ratio was 4.29 for random nanofiber, 5.78 for unidirectionally aligned nanofibers, and 7.29 for radially aligned nanofibers. These numbers shows that adding a direction to nanofibers will increase the crystallinity of the nanofibers due to the stress that happens through the electrospinning process. Here we have the lowest stress because it's random. Here we have an extra stress because of the rotating collector. But here the electrospinning process has a more tension because of the double tension during the electrospinning process. So let's go through the thermal analysis. As you can see here, all samples had a melting point at 56.8 degrees centigrade, but the radially aligned nanofibers showed another peak at 58.5 degrees centigrade, showing that it has a higher thermal stability, which is a very important character for biomedical application, because this temperature is very close to human body temperature, and if we increase this, we'll have a more stable scaffold. So if we calculate the XC, I mean the crystallinity, the volume of the crystalline phase, we can see that the random nanofibers had a 36.5% crystalline phase, unidirectionally showed a 35.4% crystalline phase, and radially aligned nanofibers had the highest crystallinity, 43.8%. This was parallel to our XRD studies and shows that the XRD studies and thermal studies support each other. Then we went through biochem. We had a significant difference between this day 7 and day 3 and 1. It shows that cells are proliferating successfully on all nanofibers, not only on unidirectionally, but in all of them. So nanofibers are very good candidates for cell culture. The red dashed line here shows the control sample, and the random nanofibers in the first day showed lower biocompatibility, but it was increased at day 7, and it has a higher biocompatibility at day 7. But if we look in more precisely, we can say that radially aligned nanofibers showed the highest cell compatibility. That is a very good results, because we can say that we had more cells, so we can confirm our hypothesis that radially aligned nanofibers signal the cells and help cells to grow faster in the direction of the nanofibers. So let's go through our cell morphology studies. Here are the surface of nanofibers. The random nanofibers are shown here. Unidirectional nanofibers are here, and measure the area of the cells using the ImageJ software, and the area was about 38,991 micrometers. For random nanofibers, it was 109,563 for unidirectionally nanofibers, and the highest number was 127 and 143 for radially aligned nanofibers. So this also supports the biocompatibility results, and we can say that radially aligned nanofibers are a very good candidate for improving the cell proliferation through nanofibers. So let's go to a conclusion. Radial and electrospun nanofibers provide greater crystallinity, which results in higher mechanical performance. They had higher thermal stability. They had a better cell biocompatibility, greater cell attachment area, and faster wound healing rate due to the cell signaling to the center of the nanofibers. And in the future studies, we are now investigating the in vivo performance of these nanofibers. And we are comparing different morphology to see that how they could accelerate this wound healing. So we had more data to talk about this structure in the future. I mean, I'd like to thank all for attending to this presentation and thank you for your attention.
Thank you for your presentation. Is there any question to Dr. Ahmed? Okay, there is no question. Thank you for your attendance. This is your certificate and we will send you also by email. Şimdi sponsor firma sunumlarını dinleyeceğiz. Hocam.
Temakla başlayalım. Would you like to make it in Turkish or English? Herkes tam uyuttuk ama iyice şey oldu. Bizim bir şeyimiz, amacımız bu şeyleri yaparken insanların özellikle bir araya gelip altyapıları da tartışıp bu sene işte sponsor sunumlarında işte biz şu şekilde projeler yapmak istiyoruz. Bu konularda şey yapacağız diye böyle bir kastımız vardı. Bundan ötürü ben de Temak'la Areka'yı sunayım istedim. So today I'm going to talk about our infrastructure, our research targets, what we are doing in Temak and the Areka company, our spin-off company. This is the last presentation. We made a trip to the lab actually. You saw most of the equipment infrastructure we do have. Just, we are going to pass together because our pizzas are ready in the garden. I am not going to keep you long. So in Temak, actually, we are targeting on the textile machinery and the materials that we can produce using this machinery. So we do have two groups actually working simultaneously and, giving feedback, and we are making the designs, machine designs according to material requirements. So we mostly focused on these energy composite filtration, separation, and biomedical industries. We are trying to produce materials in this regards. So these are some examples, actually, some small examples from our research. For instance, we can add particles into fiber structures. So this is a fiber laboratory, actually. So these are, for instance, phosphorescence particles that can be added into fibers. So in the past, we were just using, these solution-based methods, and we were trying on nanofiber materials. These are a little bit easy, you are just saying, you are just checking the spinnability. Nowadays, we do have also a compounder system. You guys probably saw in the lab trip. So the thing is, using the compounder, we are producing our thermoplastic compounds to produce modified fiber structures, meaning, and in this study in the past we did with polyurethane, thermoplastic urethane nanofibers. Right now we can do thermoplastic fibers also, these kind of mixtures, these kind of compounds, and we can produce real textile fibers, microfibers also. This is something also we want to concentrate. We do have an electron microscope, including an elemental analysis system. So if you have samples, if you are in need of the morphology things, we can help you. And also we have fiber systems. Hopefully, in coming years, we are planning to concentrate on shaped fibers. So these shaped fibers, due to their morphology, you might expect some different properties, including the gloss or including different functionalities that we can add. We are also working on surface a lot. We do have this contact angle meter. In the past, we also worked on some surfaces that repels additives, that repels stains. Whatever, considering the, biomimicry approaches, we can go for hydrophobic surfaces together. We do have all the instrumentation to go for lithium sodium ion batteries. Energy storage is a big issue nowadays. We are nowadays concentrated on separator studies, but also it is possible to produce these carbonized fibers, and these carbon fibers can act like the anodes and cathodes of the sodium and lithium ion batteries, my friends. So we do have all the infrastructure. For now, I can say that we can use our infrastructure to go for these energy storage materials. Another thing actually we served during the pandemic era is the filtration. We do have these filter testers for submicron aerosols. As I said in the beginning, we do have these nanofiber and nonwoven producing systems. Using the systems, we first produce the masks or filter media, and after that we are testing ourselves. We can go for nanofiber filters as well as electrolyte filters. So these are still hot topics in industry and academia. Another thing, for instance, we got some funding from Boeing company was in the past, we worked on photocatalytic filters. So these photocatalytic filters especially works for some gases. As you guys know, all of us became experts in air filtration side, I believe. In air, we can find viruses and bacteria, which we already noticed. In air, we may have particulate matter. In Istanbul, we really suffer. And thirdly, we might have some gases, some VOCs that are really reducing the human activities, human energy. For instance, acetone, ethanol, toluene-like materials. These materials are in gas form, and when you breathe, it is also causing a lot of health problems. So using photocatalytic structures, we can go for such filters to remove the VOCs in the environment. Even some of our companies, for instance, suffer from these VOCs that can come from industrial activities. Another thing I believe we are strong is the composite side. We can go for two-dimensional composites and three-dimensional composites also. We are producing these VARTM systems and corresponding, composites. To be honest, in academia, it is very much preferred to produce some natural, natural alternatives to carbon and fiberglass composites. So in the past, we worked a lot on this. Another thing we do have capability is these tanks actually. These are really popular materials if you check for the hydrogen storage side or different storage of the different gases. So this is a picture from our tanks actually. This is something we produce in our lab. This picture is also from our lab. This 4-dimensional filament winding system can produce such gas storage things. These guys can go up to 700 bars. There are some requirements for hydrogen. That is something we are working. And the green composites are very much preferred in transportation industry also, and also construction. I can say that if you go for carbon side, it means that you focused on performance. If you go for this green side, sustainable side, these are generally for reducing the costs, my friends. We do have a small microbiology lab as well. We can do our test, and currently collaborating with Bahçeşehir University, we are also working on some wound dressing materials as well. Another thing we actually started working in 2000s is the electrospinning. We are with Dr. Demir, we are one of the pioneers in electrospinning. After electrospinning, we also developed some systems like aerospinning, centrifugal spinning. And nowadays we are producing these systems, especially these aerospinner and nanocentrino. These are utilizing from the compressed air forces and also centrifugal forces like cotton candy system. So especially we were able to increase the system's safety plus system's productivity. I mean, especially for centrifugal spinning, we can go up to 100 milliliter per hour rates. So these are really high rates to make industrially feasible nanofiber systems. So these are lab scale systems we produce, but also we got funding from TÜBİTAK to industrialize this system. I believe yesterday you also visited our lab to see. Another thing actually we concentrated is, at the beginning of my presentation, I told you we are a fiber lab. We want to concentrate on fibers. During the pandemic area, many countries suffered to find these melt-blown fabrics. You guys probably saw actually this system also. So we concentrated on this topic because, I mean, basically what we are doing here is we are preparing a polymer solution, and this solution is blown by means of compressed air. If you somehow transfer here polymer melt, so this is called melt blowing actually. This system is very much called as solution blowing, but if you use melt, it's going to be melt blowing. So we produce this melt-based system, melt blowing system. And another thing, especially when you want to go as AXA, as my friend Aras introduced you, I mean, fibers like acrylic, viscose, UHM, ultra high molecular weight polyethylene, those are all produced using wet spinning system. So this is something also we currently installed in the lab. So we want to concentrate on wet spinning also. And another thing, maybe more environmentally friendly, is for the cases of polyester, polypropylene, we can also produce matte spinning systems, and we can work on matte spun filaments. Another thing, maybe before the pandemic, it was really kind of dream for us with Ulpas. We were inviting students all around Turkey, and we were giving some lectures actually, 2 weeks summer schools. I don't want to, give a break here actually. In summer, we do have, as you know, these 3 months breaks. And rather than these breaks, maybe we can arrange such summer schools. We can invite our friends from all around Turkey. These are undergrad students. And, many times we were selecting a topic. For instance, this year's topic can be composites. This year's topic can be filtration and separation. And we were giving these 2 weeks courses. And at that time, I want to also thank all the professors come to Istanbul and gave presentation on their expert areas. So it was something really nice as well. So far we do have collaborators in all continents actually. This is very limited number of our collaborators. Hope we are going to increase it more with your presence. I did not include our collaborators, local collaborators in Turkey. So I want to thank very much. I believe this TEMAK presentation should be more than okay. No need to go Areka. Thank you very much. So Professor Demir, Professor Olcay, are you going to give a final speech before going to Garden Pizza? No need for that. Yani we are hungry, I believe. No need. I am hungry at least.
I would like to thank Ali Kılıç for this presentation and for the whole great help all over. And I also have a certificate to Yasin. I would like to give. Thank you very much. Ben de gideyim. Değerli arkadaşlar, oturumun sonuna geldik. 2 günlük sempozyumun sonuna geldik. Öncelikle hepinize sabrınız, desteğiniz, gayretleriniz için çok teşekkür ediyorum. Son oturum, kapanış oturumu, onu da başlatmış olduk böylece. Başlatmadık. Ben kontrol ettim, aynı oturuma devam ediyoruz. Dolayısıyla belki YouTube'u değiştireceksiniz. Peki. Değerli arkadaşlar,